Thanks to all of you to be here. My name is Simone Di Muli, and I'm a PhD student at Johannes Gutenberg University of Mainz. This is the title of my talk. We will be discussing how to compute nuclear structure corrections in muonic atoms, and it is part of the project that I'm currently doing for my PhD together with my supervisor, Sunabaka. So I've included a short outline for what we are going to do. We are going to start by doing a recap of muonic atom spectroscopy. We'll go very fast there since I have to just highlight maybe a key points to help me go through with my presentation. Then we have a section with theory and numerical methods, one section with the results, and one with the conclusions. And let's jump on to the very first part, which we are going to use to introduce these systems. So till the end of the talk, a muonic atom will be a system made of a muon bound to the nucleus, one single muon bound to the nucleus by means of the electromagnetic interaction. And we want to study this system since the muon is much heavier than an electron, and this has the consequence that the Pohl radius of the muonic atom is much smaller compared to the Pohl radius of an ordinary atom. And this makes really the energy spectrum of the bound muon very sensitive to the details of the nucleus. This is the reason why nowadays muonic atoms are considered an excellent precision probe for the nucleus, and they have been extensively used over the last few years to study nuclear properties. One of these studies is the currently ongoing experimental campaign at PSI in Switzerland of the CREMA collaboration, which aims at measuring nuclear charge radii across the nuclear chart by making spectroscopy experiments in muonic atoms. And they have released already some results, starting from the muonic hydrogen experiments in 2010, going up to muonic deuterium in 2016. And last year, in January 2021, they released the results on the muonic helium-4. But in order to introduce where my part of the job is, let me tell you how they make such an extraction. So what they do is to measure an atomic transition, let's say the lamp shift. The lamp shift is one of the possible transitions, but many others are also possible. So they measure the lamp shift, the left-hand side of this equation, and then they use the fact that all the terms on the right-hand side of the equation can be obtained by theory. And one of them in particular is proportional to the charge radius. So they can invert the equation and make the extraction of the charge radius. So let's go over to this term one by one. The first one, this delta QD, accounts for all the possible quantum electrodynamic effects. These are like a vacuum polarization of the photon field or lepton self-energy. And this term can be computed with high precision, but we will not be discussing this term here because the aim of my work is compute the combination of the other two terms that are together known as nuclear structure corrections. So they came out from this type of Feynman diagram. We have a one photon exchange diagram with a form factor insertion in the nuclear current and a two photon exchange diagram. This one photon exchange diagram is very nice since its leading order contribution is factorized out indeed dependence on the charge radius of the nucleus. So these allow this extraction to be possible from the very first. But again, we will not be focusing on this diagram because our aim for this talk will be to discuss this two photon exchange term. And the reason comes from a matter of precision. Even though this term is very small, it usually accounts for roughly 1% of the total strength of the lamp shift. These numbers holds for the muonic helium-4 system. But nevertheless, when we take into account the uncertainties associated to the theory side of this equation, we found out that most of the uncertainty comes indeed from this two photon exchange correction. So this term is currently representing the real bottleneck for a precise extraction of nuclear charge radii by making these spectroscopy experiments in muonic atoms. And there are huge motivation to try to improve our computation of this term and as a consequence, reduce the associated uncertainties. So this was the end of the introductory part. I hope I've built up enough motivation to justify what we're going to do next. And next, we are going to discuss indeed how we make in minds the computation of these two photon exchange corrections in muonic atoms to the Lamb shift in muonic atoms. So let me start by saying that we do that in perturbation theory. And this one in the middle, this H mu, will be our unperturbed Hamiltonian. It is basically the non-relativistic Hamiltonian for an hydrogen atom in the Coulomb field of a point-like source. And this one at the bottom is our perturbation Hamiltonian, which basically takes into account the fact that the muon is not really interacting with a point-like source of radiation, but it is interacting with a nucleus that has a finite size, it has a structure, and it has its own dynamics. And in reality, the interaction is between the muon and the protons inside the nucleus. Later on, we will include also charge form factors of the nucleons, which among other fields will make the muon interacting also with the neutrons and not only with the protons. But for the moment, let's stick with these approximations. And this one at the top will be our total Hamiltonian, where Hn is the nuclear Hamiltonian, which is included or not, depending on whether we want to look for nuclear finite size effects or polarizability corrections. In the literature, these are sometimes known as elastic and inelastic contribution, respectively. But since in this talk we want to look for polarizability corrections, then we will include this part of the Hamiltonian in our equations. So as we do that, this two photon exchange amplitude can be, the correction of coming from this two photon exchange amplitude can be expressed in this way. We are working in second order perturbation theory, so we have two insertion of the perturbation plus a green function. This is a green function for the two-body muon nucleus system, which has this spectral decomposition, where n are nuclear states, omega n are nuclear excitations, and this epsilon mu is the energy of the bound muon. So having that said, so we can evaluate the polarizability correction. So the previous equation needs some massage, and let us also make some approximations. So let us, for a start, evaluate everything non-relativistic quantum mechanics. This means that both external states and green function will be solution of non-relativistic equations. And let us also neglect Coulomb interaction in intermediate states. After we do this approximation and we do some massage of the previous equation, the polarizability term will be expressed in this way, where these rows are nuclear transition densities, and this W is known as the leptonic part of the matrix element, which if we want, we can express as a Taylor expansion as in the following equation. So this Taylor expansion is done in terms of this eta. This eta is an operator on the Hilbert space of the nucleus. So as soon as we take the expectation value, it is a set of numbers for what concerns the leptonic matrix element, which has been argued in previous literature to hold a rough value of 0.3. We justify the use of a Taylor expansion and make it possible to obtain meaningful estimates of this polarizability term by truncating this expansion to low order. And this is exactly what we do. We make this expansion and we truncate this expansion to the next leading order in the eta expansion, this eta formalism. And these are the results that we get. So if we truncate the expansion at the leading order, we get that the polarizability correction will be equal to this delta D1. This delta D1 is basically an energy weighted integral of something that is known as the electric dipole response function of the nucleus. Then we got the next leading order. We found two more corrections to be added to the polarizability. This is delta Z3 and delta R3. And these two are related to charge densities of the nucleus. And then at the next leading order, we found three more corrections coming from three new response functions. And I just want to mention that this SQ is an electric quadruple response function, whereas this SR square is an electric multiple response functions. And then we have other corrections. So we have we neglected Coulomb distortion effect at the beginning, so we include them back in our formalities. We include only the leading order effects of these Coulomb distortion effects. We include leading order relativistic corrections and leading order nucleon finite size effect, which, as we mentioned before, they make also the muon interacting also with the neutrons and not only with the protons inside the nucleus. So yeah, maybe this is the right time to stop, since this part was quite technical and we just finished that. So maybe this is the right time to stop and ask if there are questions for this very technical part so far. So, okay, if not, I took my chances to get some water. If there are no questions, I will go on and let's take time for questions at the end of the talk. So over the last few slides, we mentioned a couple of terms that we need to compute to evaluate this true photon exchange correction to the Lamb shift in muonic atoms. And then that was quite technical. The important thing to remember, though, is that we need some inputs coming from nuclear physics. These inputs are expressed in terms of charge densities or from response functions of the nucleus, and they can be obtained in two ways. They can be obtained from experimental data, but here we want to do something different. We want to obtain this input from ab initio theory, from ab initio method. And that means that you want to obtain this input by solving first the time-independent Schrödinger equation for the nuclear states using control approximation, where control approximation means approximation that we can quantify and that are systematically improvable. And having the solution of the Schrödinger equation, then we want to build up these densities and the response function afterwards from that. So if we think about approximation from nuclear physics, we find out that they mainly come from two sides. They came from the R definition of the nuclear Hamiltonian and from the nuclear wave function, which basically is this second point is our numerical precision in solving this Schrödinger equation. We will not discuss this second point. I will just mention that we use the hyperspherical harmonics method, but we are not discussing this second point here since it's quite technical. But what we are going to do here is discuss the first point. And in order to tell you how today we quantify the uncertainties coming from the nuclear Hamiltonian, before that, let me tell you how it was done before. So what you're seeing here is a previous work on the polarizability on the true photon exchange correction in muonic helium-4 by my supervisors, Rebecca and Chen-Ji. And they made this work in 2013. And what they did was computing all these terms that we just talked about. You can probably recognize some of them, given the discussion we just had. And they computed all these terms with two different nuclear models. They have V18 plus the three-body Urbana-9. And this is a chiral effective field theory force with two-body force at entry LO and three-body force at entry LO. And at the very end, if they sum up all the possible contributions, they end up with these two numbers here for the total corrections coming from the true photon exchange amplitude. And the uncertainty they gave coming from the nuclear model was taken as the difference between these two numbers. And these had a huge impact in the theory of these polarizability corrections in muonic helium-4. And as you can see here, like they got an uncertainty that was much smaller compared to the uncertainty of the previous theory computations in the 70s using experimental data. However, this uncertainty might look small when it's compared to this scale, but it is still very big when it is compared to the experimental precision. So we still need to improve our computation of this uncertainty, and this is where my part of the job comes in. So what I'm trying to do is to redo these computations in light muonic atoms. and trying to improve the precision of these uncertainties. So in order to do that, let me tell you what are all the possible sources of uncertainty. I made a list here. We are not going to go through each of these terms individually, but let me already tell you which terms I have already reevaluated during my PhD work. These are these 2 points here. So we are going to discuss in this talk my reevaluation of the nuclear model uncertainties and of the eta expansion uncertainties. So this is what we are going to do till the end of the talk. And let's jump on to the first of these uncertainties, which is the one coming from the nuclear model. And let me tell you, like in the modern view of doing nuclear physics, nuclear interaction are derived from effective field theories. In particular, in my work, I'm using effective field theory that are known as, this is known as the chiral effective field theory, which is a low energy theory of QCD, which is written in terms of pions and nucleons as degrees of freedom. And the chiral effective field theory gives us a set of nuclear operators. This set is infinite, but we can associate a power counting scheme, and this will assess a well-defined hierarchy among the different nuclear operators. In order to understand what that means, let's take a practical example. The power counting scheme you're seeing here is the so-called Weinberg power counting, and it basically tells you that there are two operators, these two here at the top, these leading order operators. Those contributions to all the possible nuclear observable are expected to be more important to all the others, and their contribution is expected to be more important than the next leading order operator, whose in turn contribution is expected to be more important than the next leading order operators, and so on. And this separation of scale is extremely important because at some point we will need to truncate this expansion. But by exploiting this separation of scale, we can make sure that we can associate reliable uncertainty quantification to the truncation of this nuclear model, Hamiltonian model. So finally, we can discuss some of my results. And let me first tell you that there are many nuclear Hamiltonians derived by the chiral effective field theory already present in the literature. For this work, we decided to use one particular nuclear Hamiltonian, which is written in coordinate space, and it is local up to the next to next leading order. And actually, there are two formulations of this local Hamiltonian coordinate space. We are using the one that does not include the delta excitation. So this is the interaction that we're using. But before using this interaction, we needed to implement that in our computational machinery. And all the time that we implement something new in our machinery, we need to do some benchmark tests to make sure that the implementation has been done consistently. So what you're seeing here are our benchmark tests in helium-3. These are nuclear helium-3 and helium-4 systems, and we are computing ground state energies and charge radii. And we are benchmarking against the available green function Monte Carlo results. So the green function Monte Carlo results are these colored bands. There are two colors because this interaction comes with two different cutoff at 1.0 and 1.2 Fermis. And our results are these triangles. And in order to compare the plots, you should really look at this Kmax 22 because it represents our most precise computation. And you can clearly see that there is an excellent agreement. You might think that there is a slight disagreement here in the binding energy of the helium-4 for one particular choice of the cutoffs, but this difference is very small and it goes away as soon as we include also the precision of our numerical model, numerical machinery. So now that we have a working interaction, we can use that to compute the two photon exchange term in different ionic atoms, and we started with ionic helium-4. Again, you can see on the left-hand side of the slide our computation for all the possible terms that they made up the two photon exchange term, and we did the computation with the two different cutoffs. And on the right-hand side of the equation of the slide, you can see the convergence pattern for this observable as we increase the order of the chiral expansion. The horizontal dashed line are the previous results by Chen Ji and Sonia Bacca. And in general, I found an excellent agreement with them using this new interaction. So here, the uncertainties are evaluating using the Applebaum-Krebs-Meissner recipe. But I think we can do, in current days, nowadays we can do better, and probably we should. So we evaluate the uncertainty also using Bayesian techniques, which is, this is the results you're seeing in these other slides. And these Bayesian techniques allows us to get the full probability distributions for the two-photon exchange term. And we can use this distribution to highlight also the 68% and 95% confidence interval, which are highlighted in these plots as the dark and light shaded area. So let's look directly at our most precise results. This one at the next to next leading order. And again, I found an excellent agreement with the previous computations by Chen Ji and Sonia Bacca in 2013. So please don't pay too much attention for the moment at these uncertainties at the leading order. I believe they should not be trusted, and I can argument that later on if you have questions about that. So these uncertainties at the leading order should not be trusted, but these as the next to leading order, and more importantly, at the next to next leading order, can be trusted. Okay, so this was the end of our reevaluation of the uncertainties coming from the nuclear model. So let's discuss the other uncertainty source, namely the at expansion. And what we did was, again, employing Bayesian techniques to reevaluate these uncertainties. What you're seeing here are probability distributions for the truncation uncertainty in that expansion. These are uncertainty related to the truncation of the next to next leading order in that expansions. And these are already expressed as a percentage of the total polarizability corrections. Probably you can better appreciate or work from this table. These are the uncertainties that we got. And we can compare this uncertainty to the previous work already present in the literature. And you can probably see that there seems to be a problem in Munich helium 3. So we found an uncertainty that is more than 4 times larger as it was quoted before. And in general, we believe that these Bayesian techniques, this particular Bayesian techniques gives us slightly conservative uncertainties, but this really does not justify such an increase in the uncertainty in Munich helium 3. So probably that expansion in these Munich atoms converged much slower than what was previously expected. And it will be good to reevaluate this polarizability correction in this Munich atom using a formalist that does not involve at all this at expansion. So I think I raised a hand here. So these are my conclusions. So we have time. Yes, I think we have some time. So we talk about ab initio theories, and I hope I've shown you that they represent an excellent framework to calculate nuclear structure effects in Munich atoms. We reevaluated the uncertainties coming from the nuclear model and from that expansion using Bayesian techniques. We didn't really succeed for the moment in reducing the current uncertainties, but this work really paves the way for future improvements. We found out that we need higher order computations in the chiral expansion to improve the precision coming from the nuclear model. And probably for the Munich helium 3, we need to redo a computation of the polarizability without using this at expansion at all. So thanks a lot for your attention, and please let me know if you have questions.
Thank you very much. Are there any questions at this point?
May I ask a question?
Of course.
Okay, hi. So you showed the uncertainty from bias analysis. So I want to know this uncertainty is from the truncation chiral force, or I mean the low energy constant, or from the many body truncation when you solve the Schiller equation?
Are you talking about this one or this?
The previous one. Yeah, this one.
Yeah. This one is only for the truncation of that expansion. And so this does not involve low energy constants in the interaction. It's just on the truncation of this expansion. Where is that? Here. So we evaluate this expansion up to the next leading order. These other terms which are highlighted with the dots are not evaluated explicitly. So we basically truncate this expansion, and that one is the uncertainty coming from this truncation.
I mean the nuclear structure calculation.
The nuclear structure uncertainties is not related to this one. The nuclear structure uncertainty is this one here, because these uncertainties here, maybe it's better to show this plot here. These are the uncertainties coming from the nuclear structure uncertainties, yes, coming from the nuclear model. So these uncertainties here come from our truncation of the nuclear Hamiltonian in the chiral expansion. So these one are the one related to the nuclear structure uncertainties.
Sorry, so I mean these two lines are given by two totally different nuclear force. So
indeed, yes.
I don't know if we can use this as an uncertainty. I mean, when you go to the previous slide, which you show the Bayes analysis.
This one?
Yeah, that one. Yeah, this one.
Mm-hmm.
So you have a distribution. So I wonder, how did you get this distribution? Did you change the low energy constant around the low energy constant for those force, chiral force?
No, this is not what we do. Like now I should have included like a backup slide. So, but this uncertainty does not involve the low energy constants of the Hamiltonian. It involves the fact that at some point we need to truncate this expansion. So for the moment we are truncating this expansion of the Hamiltonian at the next leading order. So this line here. So this uncertainty takes somehow into account the fact that there are all of these other operators that are not explicitly included in our computations. So it's quite technical to tell you like exactly how this is done, but this is the meaning of that error bands. And that one does not really involve the low energy constants that appears up to these orders, up to the NHLO.
Okay, thank you.
No problem.
So we have two more people that raised their hand, and that's Paul, Reinhard, and Christoph Pachucki. Maybe, but keep it short, please. Go ahead. Paul, maybe first.
I hope I have a short question. The question is how long the answer will be. What is the largest nucleus you can presently compute with your techniques?
For the moment is this muonic helium-4. We are trying to get to the lithium, so lithium-6, and I've been trying to do that for a while. It's difficult. I think we can get there with some work, but we are not there at the moment.
Thank you.
Thanks to you.
So the next question is, what is the main contribution? What are the main contribution to the uncertainty in helium-4 and helium-3? The contribution, the uncertainty for the nuclear contributions to the isotope transition.
You mean that comes from this plot here?
I mean, much beyond the two-photon exchange, because it is not the only contribution. I mean, what is the uncertainty? What is the main contribution to the total uncertainty, not to the uncertainty due to two-photon exchange?
Okay, you want to know only the one coming from nuclear physics, or also the others, like three?
No, I mean, just what is, if you would present the results, you have some uncertainties. So what are the main contribution to the incentives for the nuclear contribution to the 2s2Pi transition?
For sure, like I will say that this nuclear model and the nuclear models are together very well important. So this nuclear model comes from.
So in your opinion, the 3-photon exchange doesn't contribute to the uncertainty?
No, it does. It does. So for the moment, we are evaluating everything up to Z alpha to the 5th. This is what you call 2-photon exchange. Z alpha to the 6th is also an important contribution, which is not evaluated yet in Munich Helium 4.
So do you have now the uncertainty for your total theoretical predictions?
I don't have the uncertainty to Z
I
alpha.
see. That is the answer. Thank you.
So thanks for the invitation. It would be great at this hopefully nice weather to be all together in Trento. Let's hope for another situation. Now we are sitting everyone in his office and hopefully listening. Okay, that is the title of the talk, and that is the menu. So I will first give you a little introduction about the theory beyond, and then I make a guided tour through the progress in developing nuclear density functional along data on radii. The first two are, example 1 is from the 1980s, example 2 is from the 1990s, and the last 3 examples are rather recent. And because I always forget at the end, of course, due to time, I put my acknowledgement right in the beginning here. And the only point is I did not know how to acknowledge experimental colleagues. There are so many, and the list of the authors is so huge that I surely miss some. So I acknowledge facilities, as you see here. Okay. First, a little bit of theory, not too much, hopefully. We have a nuclear density functional theory, quite general. You have a function for given model parameters, which depends on the density, kinetic density, spin orbit density, and pairing density. And once this is given, you derive equations of motion variationally. That is all known to theorists, and everybody else need not to know it. What we need to know is that those models have typically 12 to 14 free parameters, and we have very little instructions from ab initio models how to fix them. So we tune them to a couple of empirical data I explain later. This chi-squared fit, which is probably better known to the experimental colleagues here around, gives us first optimal parametrization, but there is more in it. We can add to it a statistical interpretation, and then we obtain uncertainties of our predictions and statistical correlations, which will turn out to be very useful. So today's talk concentrates on the effect of radii on the development. Oops, there's a question. Yeah. Somebody is raising their hand, or is this without any meaning? Okay. I will use statistical analysis as a navigator through the landscape of model parameters. There's one experimental theoretical detail which I have to emphasize. I will use 2 functionals. The traditional Skirm functional, which has a density dependence, a kinetic term, a surface term, spin orbit term, and the Fayence functional, which is very similar to the Skirm functional and has in addition a gradient term in pairing. I spot that here quickly. The black part is what you have in Skirm, and the new piece by the Fayence functional is a gradient term, so to say, a surface term in pairing. So that is how it works. You have a model with a couple of parameters. You crank the mill and obtain any observable you want as function of the parameters. Then we take a selection of experimental observables, build the mean square error, and because we have different dimensions, we take energy, radius, etc., we need to calibrate, we need to put weights on it to make this dimensionless. That means we have an adopted uncertainty for each observable, and the rule of adopting it is to have a chi-squared per data point about 1. So this, you know, we minimize chi-squared by different techniques to be sure. And the pool of data that's important are bulk properties of nuclei, binding energies, radii, and there are 2 of them. There is a root mean square radius, you all know, and there is a box equivalent radius, which you get in electron scattering from the diffraction radius, and a surface thickness. We add a sprinkle of spin orbit information, and for pairing, the odd-even staggering of energies. That is well-settled stuff from the 1980s, 1990s. And now, lately, we decided to add more detailed information on the differences of radii, which are very well measured those times with isotopic facilities. So that is a statistical interpretation. We take the chi-squared, you have already seen, and say the exponential of that is a probability distribution for the reasonable parameters. The optimal parameter set is the minimum of chi-squared, the maximum of the probability, and we have a range of reasonable parameters which is defined by enhancing the minimum chi-squared by 1. And this probability distribution then allows to compute by standard techniques averages, more interesting, variances, that is the uncertainty of a prediction, the allowed uncertainty of a prediction, covariances from which we can compute statistical correlations or the coefficient of determination. I remind you, a coefficient of 1 means fully correlated. 1 is fully dependent, A is fully dependent on B, the other one is fully, 0 is fully uncorrelated. Das war for theory, and now we jump through the application examples. First, just the radii on bulk ground state properties. Here, I start with taking only energy data and tune the model, only energy data and the fit, and I look at the radii data as prediction. We get, rather surprising, at once a very good description of charge radii by fitting only energies. Nice, but the form factor, which is here parameterized in terms of box radius and surface thickness, is awfully off the line. So here's the goal, the line, the middle line is where we should go, and we are far off. Now we can invoke statistical analysis. What is a predicted error, the predicted uncertainty? Here's the average of the prediction, quite correctly, and here is the uncertainty. And we see that the uncertainty band hits the wanted value. Conclusion, we have good chances to fit the box radius and surface thickness once we include the data. That's done here. The red dots are all included, and we have much better description of the form factor in terms of box radius and surface thickness, and not much of a loss or sacrifice on the other data. So that is the state of the art, 1985. What does it mean for extrapolations? And I look here as one example, extrapolations to very neutron-rich tin, which are crucial in the art process chain. Green is the fit to energies only, red is the fit to energies and radii. And you see immediately that the error band, green area, red area, is dramatically reduced by adding radius information. for the prediction of binding energies. And mind, this is not binding energies as such, it's binding energies by a very curious size, power one quarter, because I wanted to fit everything in one scale. And here are the radii, and obviously we include radii in the reduction, and the prediction of radii is much better. Okay, let's go on. 1990s, there was a big discussion about a kink in the radii in the lead isotope. Here is a magic lead 208. Below we have a slope, above we have a larger slope. That's the experiment. All Skirm forces, I take here one out of many, just go straight through, no kink, you can do what you want. And the relativistic models at once get it. So we looked at it with statistical analysis. There is a chance to have pairing, a chance to explain it by spin orbit. We now looked at the theory and this that revealed that the relativistic model has a different spin orbit structure than the non-relativistic Skirm model. We mapped the spin orbit structure of the relativistic model to a non-relativistic Skirm model, and so with the spin orbit extended Skirm model, we get the kink as well. So radius information is crucial for model development. In that case, it has revealed a missing term in the model, a missing feature. Now we come to the more recent results. There was a problem with the odd-even staggering and isotopic shifts in calcium isotope. Here is the problem. Like again, the data, the isotopic shifts in the calcium isotopes relative to calcium-40. And the red is a Skirm result, and you can take whatever Skirm force you want, even the nu with a proper spin orbit, isovector spin orbit, you go straight through. No chance to get it. Now let's ask theory, do we have a chance by refitting it? So I look at the uncertainty of the prediction. These are the error bars here. And this is far off. There is no chance to fit with a given model this isotopic shift. It would destroy the quality of the model, the error bar. The allowed variations are much too small. So we have to do something. And where should we look at? So the first chance is, are there ground state correlations, collective vibrations? You know that calcium isotopes are soft vibrators, at least this one here. So the green curve is mean field plus ground state correlations. Well, it helps, but not enough. So what else? How can we improve the model? Where are the handles? And here is a correlation of the isotopic shift with different model features. Look at the number, 30% correlation is not much at all. So that means isotopic shift is composed of different contributors. The symmetry energy is one of the large. The spin orbit splitting, as we know already, is another large contributor. And the largest is pairing. Okay, symmetry energy, no chance, that's fixed by polarizability. We cannot play around with that. Spin orbit splitting, one could play, but it's unlikely because that's fixed by lead 208. So pairing is our chance. So we go for playing around with pairing. And now we come to this Fayence functional, which has another degree of freedom in pairing, which is missing in all the Skirm functionals. And adding that, a gradient term in pairing gives us this green result. It solves the problem. Another example where radius data have helped or revealed missing features in the model. Next examples. We continue with isotopic shifts and odd-even staggerings, but in heavier nuclei. So that is a heavy figure. Don't look at details, just take the taste. Here we have the experimental data, again black. That is the isotopic shifts you had seen already, here enriched by odd isotopes. And then you see the odd-even staggering. And down here, we amplify the odd-even staggering by taking the third difference, and it's not so good. It's overestimated by the present fayence fit. Even worse, for the tin chain and for the lead chain, we have a systematically wrong trend. So something is missing here. And we have done the same statistical analysis as before, and we see that all these quantities which we want to tune are highly sensitive to pairing. Then we have to look so that the statistics is not a black box which you just crank. Then we have to think what is missing in the theory, and then we realize that the fayence pairing functional so far had only isoscalar term. So we add an isovector term. These are the green points, and to make it more shiny, I make the other ones, the wrong ones, less brilliant. Okay, so that is a great progress. That is a picture from last week, by the way. And with adding an isovector term, we can accommodate the odd-even staggering, the trend here. Still some problem with odd-even staggering for tin chains, but it's a great progress. And another example that these careful measurements here, tin 134, and down here, and in the lead 214, etc. These careful measurements from isotopic facilities helped us enormously to blame the models and then to improve it. Let's see what does it with extrapolation to our process nuclei. I take the same example as before, fit to energies only, green as before, fit to all energy and already form factors, red as before, and the new fit in blue is where I include fayence pairing with isoscalar and isovector pairing and gradient terms. So yeah, the errors here are a little bit smaller, not too much. It's better for the radii still. So the improvement or the precision, reliability of the prediction has not too much been improved, but we see interesting results here that the trend is different. And that means that to fix that, to decide what's really better, we are eagerly waiting for, if possible, more measurements towards more neutron-rich nuclei. So, but still something is missing. Where could we get more information on neutron-rich nuclei from? What neutrons? Why not measuring the neutron radius? All of you know that is by no means easy and very expensive. There is this neutron radius experiment in JLab, and that's the final point I want to come to. So the photon, the lead radius experiment, PREX, that scattering of very energetic electrons polarized, from which you deduce the parity violating asymmetry at a certain transferred moment of .4 inverse Fermi. The alternative to measure, quotation marks, neutron radius is to look at the isovector dipole polarizability. That means you measure the gamma absorption cross-section and the polarizability is then weighted integral. It's simple in principle. It's a problem that you have maximum energy, and what's missing here in the integral is the source of uncertainty in these results. So why are these things measurements of the neutron radius? Well, here I look at statistical analysis and evaluate with a model, with many models, by the way, to be sure, the coefficient of determination, the correlation between the parity violating asymmetry, the polarizability with the neutron radius. And look at that. Here we have correlations 99%, 98%, can't be better at the level of this analysis. That means measuring the parity violating asymmetry and the polarizability means measuring the neutron radius, however model assisted. Okay, let's look what happens. This is the experiment in the plane of polarizability and parity violating asymmetry with considerably large error bars, let's say convenient error bars. Here is the target, so to say, the goal we want to hit. And here I take a lot of Skirm forces I have in my shelves, and I take a lot of relativistic models I have in my shelves and draw them in that plane, and just picked only a few of them to make it better visible with systematically varied symmetry energy. And they all line up nicely, but none of them hit the goal. They systematically avoid the goal. I did it also here with the best fit, and the area, the green and the red area, shows you the probability distribution in the plane of polarizability and symmetry violating, parity violating asymmetry. I never get it. Yeah, so we have a dilemma here. We have two measurements, and no theory so far is able to harmonize them, to hit this point. So that means the neutron radius we derive from the polarizability down here is smaller than the neutron radius we derive from the parity violating asymmetry. But polarizability would be here, parity violating asymmetry would be here. We have two different mean field models, and these give much different radii. So we have a dilemma here, and we would like very much to know the neutron radius, but at present we have first to solve that problem before we can use it for model development. I come to my conclusion. Radii from exotic nuclei, as I hope I've convinced you, are extremely crucial for nuclear DFT developments. They deliver valuable data for better confining models, and they challenge, not to say blame, the models by revealing missing features. Future, we need just more of that, just to make the extrapolations to our process nuclei more reliable. That would be very nice to have a little bit more of the very neutron rich. And last not least, the information on the neutron radius is highly wanted, but still enigmatic. Okay, that's all for today.
Thank you very much for that nice talk. So are there any questions at this point? Yeah, if you raised your hand, just go ahead and, yeah, Wilfried maybe first, because for whatever reason.
Okay, thank you very much for this very nice talk and the didactic introduction. I have a probably naive question on slide number 8, which shows the uncertainty bars in the radii that you had just after the energy taken into account. And I wonder how these error bars come about. Is this just the distribution of the scattering there? But then, of course, if you have a single one hitting the 0, your error bar will always hit the 0. And it also does not look like a typical statistical uncertainty where you would expect something like 2/3 of the.
No. The error bars comes not from these data. It is extrapolated from the fit of the energy data. It is, as I told you, hopefully, here, you have a chi-squared from your energy fit, and the error bars is the average of this distribution over the radius prediction. Yeah, so this is an extrapolation error from statistical technique. And it's extrapolation because energy was fitted, box radius is predicted. Does that answer?
Okay, thank you. Yeah.
Sonja, do you have a question?
Yes, yes. I wanted to ask you regarding the last figure you were showing. So it is the correlation of the party vibrating asymmetry and the polarizability. I would get this very same information if you plotted the neutron radius or neutron skin, right? On the y-axis. Yes. This was one question, and second is how do you get from a density distribution calculation to the party vibrating asymmetry? Is every functional is treated in the same way? What is the machinery in it?
The machinery is, we decided to compute the parity violating asymmetry forward. So we have a model with given parameters. We plug in the parameters, get proton density, neutron density, and then we add information with some uncertainty about the weak. Then we charge of the proton, of the neutron, and all these corrections at the talk in itself. So it's really a forward calculation from the model to the APV. Nothing in between.
But don't you have to make an assumption on the diffuseness of the density distribution? No, you just
diffuseness is result. The diffuseness is result of the calculation. We make an assumption about the diffuseness of the microscopic nucleon contribution. So we take the nucleon form factor from the MINDS data, the old MAMI data, and the neutron form factor, and a little bit of information from the strange quark.
Okay.
I found rather uncertain. Okay, whatever. But the whole machinery is involved here, and it would take me 20 minutes to explain it.
No, that's fine. But so it is equivalent as plotting it versus the skin or versus the. So on the y-axis, I could put the skin or the neutron radius and get the same information.
Yeah, because within the models I had shown you, the correlation with neutron radius and skin is almost 100%. So plotting APV or the other thing is the same. But I knew that only after I have decided to compute APV.
Okay, thank you very much.
Okay, we have one more question. Maybe back.
Hey. Yeah, hey, thank you. Very nice talk. I have a quick question about the isovector pairing term. Yep. Maybe I missed something, but it made the agreement, for the tin and the lead pretty good. But it seems to me it made the calcium agreement, for the radii a little worse.
You mean this figure?
Right.
Which radii are less good?
No, okay. Calcium is also improved.
Yeah.
As well. Okay, got it.
Okay, yep. You always find a point which is worse than before. That's the deal. So the chi-squared is a compromise, and you make a different compromise, and some lose, some win. The point is more win than lose, and that is progress.
Okay, well, thank you.
Good afternoon. First of all, I would like to thank the organizers for asking me to give this talk at this workshop. I'm honored to have this opportunity to introduce our recent progress on the precision spectroscopy of the lithium ion, especially in the presence of such a lot of distinguished physicists. So as the title says, in this talk, I'm going to give an example on determining nuclear property from high-precision atomic spectroscopy. This research is part of a long-term collaboration between two terms from CAS APM that work on experiment and theory respectively. Members of the experimental team are listed in the first row of the name list, and in the second row are the theoretical team. So, firstly, I would like to give a brief introduction on the motivation and the background of our research. So why do we study the lithium ions? The first reason is that as is known to all, spectroscopy of few electron atomic systems allows very accurate theoretical calculations and plays an important role in modern physics. Not only does it provide a stringent test of the QED theory, but also can it be used to probe nuclear structure, determine fundamental physical constants, and search for new physics. Secondly, the lithium ion has the same electron configuration as that for the helium. Thus, it may serve as an independent test for the theory of helium. On the other hand, lithium has a heavier nucleus. Thus, it presents more prominent relativistic effect as well as nuclear structure effect. And besides, both stable isotopes of the lithium presents rich hyperfine structures, which could be advantages for determining nuclear structure properties, as well as isotope shifts. Finally, from the experimental point of view, a narrow 9-wise laser for the 2s2p triplet transition is easy to access. So, the spectroscopic accuracies of the lithium ion up till now are listed in this table. It can be seen that generally the accuracy of experiments of the lithium ions, especially for that of the lithium-6, does not match that of series. So further work needs to be done. This is even truer when we compare the research status of the lithium ion with that of the helium atom. So in this talk, I will focus on the hyperfine structure of the lithium ions. First, I will give a brief description on the theory of the hyperfine structure of the lithium ions, and on how nuclear structures, say the Maha radius, could be obtained by combining theoretical and experimental results. Our theoretical treatment on the lithium ion hyperfine structure is similar to that of Pachucki on helium-3 atom. As is shown, we expand the effective Hamiltonian of hyperfine structure in terms of alpha. Here, the first term is effective operator responsible for the fine structure splitting in the absence of the nuclear spin. The second term is the leading order hyperfine Hamiltonian with recoil and anomalous magnetic moment additions, and so on, up to the order M alpha 6. And for higher order QED corrections, the hydrogenic approximation is used in our calculations. For this work, what we are mostly interested are the last two terms, which represent the contribution from nuclear structures. So one contribution comes from magnetic moment distribution of the nucleus, which features as the Riemann radius, REM. And it can be expressed by this equation. The other contribution comes from the nuclear electrical quadrupole moment, and here is this expression. All the above terms except the Riemann radius can be calculated with high precision. Thus, if a high precision experimental value of the hyperfine splitting is available, we can obtain the Riemann radius. Now I shall turn to the experimental part. First, I would like to describe our previous work on the lithium-7 ion based on the saturation spectroscopy. So before our work, the latest experiment was conducted by Clark and co-workers using a method they called Nebula. They intersect a lithium beam with an UM-modulated laser at a small angle. By scanning the driving frequency of the UM, they got a spectrum like this. Because the line shape was unsymmetrical, they scaled the amplitude of one peak and shifted its position to obtain an optimum overlap. In this way, they get the hyperfine interval. Due to the unsymmetrical line shape, frequent reloading of the lithium samples, and a very broad line-wise, the precision of their experiment was not very good. On the contrary, by using the saturation spectroscopy, we were able to eliminate the Doppler broadening and obtain a NAM-deep signal with symmetrical line shape. So to give an example, here I show how a hyperfine interval, which is delta F in this energy level graph, was measured in our experiment. So transitions labeled as I and L in this graph were measured alternately, and the spectra were recorded as NAM deeps, and like the upper right figure. And an interval is derived from each two consecutive spectra, and hundreds of results were averaged to get the final value with a statistic uncertainty of several tens of kilohertz. So there are various systematic effects in our measurement, which I shall describe briefly and evaluate. First, the first and the second order Doppler effect due to the movement of the ions are important sources of error in the measurement of absolute transition frequency. However, since what we concern about here are the hyperfine intervals, that's to say the difference between two relevant transition lines. So the Doppler shifts are almost cancelled due to the subtraction of common model errors. And optical loss in the laser beam path may cause asymmetry in the Zeeman components and cause a shift of the line center. However, our calculations show that for the residual geomagnetic field in our experiment, this shift is negligible at the present level of accuracy. And next, we are consider the interference of the laser power. So the angular velocity distribution of the ions may cause a power-dependent asymmetry and there's a shift in the line center. Thus, a series of measurements were conducted with laser power ranging from 20 to 40 milliwatts. And we found no shift beyond the statistical uncertainty. We finally assigned an upper limit of the power-induced uncertainty to be 11 kilohertz, and the quantum interference shift. So it has long been recognized that the line center of the resonance can be affected by the presence of a neighboring resonant transition. For example, in this figure, the interference effects between states 2 and 3 may cause shifts in the resonant frequency for driving population to state 2. It turns out that this quantum interference is non-negligible in high precision spectroscopy. For example, in the 2s4p transition frequency measurement of the hydrogen atom conducted by Bayer and co-workers, the line center of a spectrum fitted without considering the quantum interference exhibited a strong laser polarization dependence. In their work, they took into account the quantum interference and found that the real line shape should be a final void line shape. By fitting the experimental data with this line shape, the shift was drastically removed. So in our work, we also used the final void line shape to fit the experimental data, and as can be seen from the right half of the residues of the final void fitting are more symmetrical. It proves that it is a better fitting. So we believe that quantum interference in our experiment was largely removed by this way. So here is an example by taking consideration of all the systematic effects discussed above. We gave our experimental results for one of the hyperfine intervals together with the uncertainty budget. It can be seen that the main source of error comes from statistical uncertainty and the quantum interference. So here we show the complete results of our experiment. It can be seen that for the hyperfine splitting of the 2p triplet state, our experimental results are 1 order of magnitude more accurate than those of previous measurements. And our results has a similar accuracy to the recent theoretical values. And combine our experimental results of the S triplet hyperfine splittings with those of theoretical calculations, we obtained the Weimar radius of the Nissen-7 nuclei. It is confirmed that the Weimar radius of Nissen-7 is about 40% larger than that of Nissen-6. So now let's take a second look at the saturation spectroscopy of the Nissen ion and see what are the main restrictions. First, although the Doppler broadening is basically eliminated, there is still significant transit time broadening due to the ion's faster velocity. As a result, the NAM dip we obtained has a broad line-wise of about 50 megahertz. That's far beyond the natural line-wise. This results in a great statistical uncertainty, as has been shown above. Besides, according to the rule of thumb, which is often used to estimate the magnitude of quantum interference, the shift caused by quantum interference is proportional to the square of the obtained line-wise, which implies that the quantum interference might cause severe line distortions in the saturation spectroscopy. And finally, the saturation spectroscopy method does not apply to the Nissen-6 as well as to Nissen-7 because the Nissen-6 has smaller hyperfine splittings and some of its spectral lines overlap even after the reduction of Doppler broadening. So in order to solve these problems, we have to further narrow the spectral line-wise, and this leads us to a new method, the optical Ramsey spectroscopy. So we all know that in radio frequency spectroscopy, the Ramsey method is extensively used to reduce the transit time broadening. So its optical analog, which was first realized in experiment by Berquist, has also been used in laser spectroscopy for a long time. In its original form, atoms passes 3 equally spaced standing waves, and the resulting line shape would exhibit an interference fringe pattern. In this work, we took advantage of this method to measure the spectra of the Nissen ions. So a schematic of our experimental setup is shown here. As we see, the 3 parallel and equal distant standing waves of laser beams were obtained by using 2 cat's eye retroreflectors. And in the optical Ramsey method, the spectral resolution is limited by the travel time between radiation zones, rather than by the transit time through each zone. So through adjusting the interval between adjacent radiation zones, we obtained Ramsey fringes with line-wise of about 5 megahertz, which is close to the 3.7 megahertz natural line-wise, and that's much narrower than what was obtained in the saturation spectroscopy. So it is seen that the optical Ramsey spectroscopy, the spread of a distribution is much smaller than in saturation spectroscopy. The statistical uncertainty was quickly reduced. In our experiment, statistic uncertainty below 10 kilohertz is generally achieved after 100 to 200 measurements. So now let's consider the systematic errors. For the Doppler and the Zeeman effect, the evaluation is much the same as that in saturation spectroscopy. So I should just skip it. For the quantum interference, here the fellow void fitting is not applicable, and we use the rule of thumb as an estimate of the upper limit of the quantum interference shift, and we take the estimated value as the uncertainty. As a validity check, we did an experiment in a similar way to that of Bayer's work on the hydrogen atom. That is, we took the optical Ramsey spectra at the various laser polarizations and fit them without considering quantum interference. We found that the amplitude of the fluctuation was about 2 kilohertz, which is close to the value obtained from the above equation. So we just believe that our estimation of the quantum interference is reliable. And the measurements were carried out with laser power ranging from 3 to 10 milliwatts. We found no shift beyond the statistical uncertainty, and we assign an upper limit of the power-induced uncertainty to be 5 kilohertz. So after taking into account the statistical and all the systematic uncertainties, we obtain all the hyperfine splittings of the 2p and 2s triplet of lithium 6 and 7, as shown in these two tables. We see that for lithium 7, our experimental values for these splittings have uncertainties of about 10 kilohertz, which represent the most precise experimental values to date. For the lithium 6, uncertainties are somewhat larger because of its smaller hyperfine splittings, which might induce more significant quantum interference effect. So up till now, few high precision experimental values for the hyperfine splittings of lithium 6 ions were available. A recent work by Clark claimed that their uncertainties range from 0.5 to 0.8 megahertz. which are much larger than those of theoretical calculations. Besides, as can be seen, their results do not agree well with theory. On the other hand, all results have improved the accuracy by a factor of 20 to 50, and our results are in good agreement with theoretical values. For the lithium-7 ion, comparing our experimental results with those derived from the saturation spectroscopy, we can see that they generally agree well. But results from the optical Ramsey method have improved the accuracy of those from saturation spectroscopy by a factor of 5 to 10. Besides, it is noted that a discrepancy between the experimental and the theoretical value of this Haber-Phi interval has been resolved with our new value supporting the theory. So, combining our experimental results of the Haber-Phi splittings of the S-duplicate state with the most recent theoretical calculations based on QED theory, the Maha radius of lithium 6 and 7 are determined. We can see that our results agree well with the recent values from spectroscopy, but the value derived from lithium 6 spectroscopic data differs significantly from that derived from nuclear physics. So up till now, the spectroscopy of the lithium ions have been almost exclusively performed with an collimated ion beam, while the Doppler effect puts a restriction on the measurement accuracy, especially that of absolute frequency measurement. So in order, one method to reduce the Doppler effect is to use.
Sorry, I think we're running out of time. Can you finish in about maybe 1 or 2 minutes?
Yes, I finished in 2 minutes.
Okay.
One method to reduce the Doppler effect is to use cold lithium ions as an object of measurements. So in order to achieve this purpose, we are planning to prepare cold metastable lithium ions by synthetic cooling of lithium ions with net cooled barium ions in a linear power trap. And this is difficult because to perform synthetic cooling with good efficiency, we need to produce metastable lithium ions with high yield. We hope that we will find a practicable way in the near future. And so, as a summary, here is a summary of my talk. And so Here the first row are the experimental team, and the second row the theoretical team. So we will our acknowledgement to all of them. Thank you. That's all.
Okay, yeah, thank you very much. I think we can have time for one question. So Randolph, you can ask your question.
Yes, thank you. Do you hear me?
Yes.
Yes.
Yeah, okay, good. So I'm wondering for the quantum interference shift, when we found this in the Bayer paper, I mean, this Fano-Vogt fit is just a Taylor expansion of one resonance around the other one. But with your overlapping hyperfine splittings, you may have different effects as well. So how do you assign this uncertainty for quantum interference? Is this just the difference of the normal fit and the fit with Fano-Vogt, or how do you evaluate this? Because you can calculate this using optical Bloch equations in principle.
Yes, principally we can calculate the effect, but because the hyperfine structure of the lithium ion, the calculation would be very complicated, and for the time being, we are not able to do that. So experimentally, we use that method by changing the polarization of the laser and see if there is a significant shift of the interval.
Okay, thanks. I mean, in atomic lithium, this is a megahertz, the shift, right? So this is the measurements from the NIST group. So I'm a bit astonished by the smallness of this correction.
Yes, for the absolute frequency, there may be a megahertz never shift, but here for the hyperfine interval, we found that it is small.
Okay, so now let's move to the next talk.
So I would try to present the overview, how we account for nuclear structure effects in most in electronic atoms, and I will present some small references to the muonic atoms, just to complement the previous talk. How we imagine the nuclear structure contributes to the atomic energy levels. We think we have, in the simple picture, nucleus has a finite charge distribution, which is described by this rho E, also finite magnetic distribution. And this finite electric charge distribution affects the Coulomb interaction. The Coulomb interaction is no longer a point-like particle. The nucleus is not a point-like particle. So the Coulomb interaction is changed by this additional factor GE, which is a Fourier transform of this electric, of this charge distribution in the coordinate space. So once we have this, so we think that we imagine as a nucleus as a rigid body with some fixed distribution of charge, modify the Coulomb interaction, and solve the Dirac equation or the Schrödinger or Dirac equation in such a modified potential. And from the solution, we observe a shift with respect to the point nucleus. And this shift we regard as coming from the finite nuclear size. The shift in energy is a function of the fine structure constant alpha. So it is convenient to perform an expansion in this fine structure constant alpha and interpret separately each term of this expansion. So when we perform delta EFS is this finite shift of the energy, atomic energy levels due to the finite nuclear size. So we take this shift and perform expansion in the fine structure constants alpha in Z alpha. The leading term is Z4 means Z alpha to the power 4. E5 means Z alpha to the power 5. E6, Z alpha to the power 6. In the leading order, the energy shift is proportional to the mean square charge radius of the nucleus. And this is the very interesting result, because this means that when we compare theoretical predictions with experimental result, we can detect, we can obtain the mean square charge radius of the nucleus. One of the reasons is that other contributions, E5 and E6, are much smaller for electronic atoms. They are so small, they are almost negligible for light atomic systems. For heavier atomic systems are no longer negligible. But for muonic atoms, they are essential. What Simon has, I'm not sure if I pronounce his name very accurately, but in his previous talk, he mentioned this two-photon exchange, which is in German C5, and it has a significant contribution. But in the simplified model, when we treat nucleus as a rigid body, this shift in the alpha factor, the contribution is given by the third Zimach radius. It's called, or sometimes it's called rather Frey radius. It's probably the proper name. It's the convolution of the charge density of the electron multiplied by the 1 minus R2 cube. So it is a very simple formula which describes delta E5. For delta E6, it's also relatively simple, but the formula is too complicated to write down, so I'm not writing it down. The point which I would like to make is that this picture is oversimplified. That in the true world, the delta E5 is not given by this third Zimach radius. It's only because we obtained it because only it appears only because our simplified picture of the nucleus. In the more realistic picture, which is on the next slide, one has to take into account the fact that this charge radius of the nucleus comes from the individual protons and also, in some sense, also due to neutron. So if we perform an expansion of the finite of the nuclear structure contribution powers of the alpha, then the leading term, as in previous slide, is the same. It's always mean square charge radius. But the higher order terms are completely different. I mention this because in most of the literature, people are not aware of the fact that the simplified model of the rigid charge distribution is not valid. It only works for the leading order. For higher order terms, the alpha, the true energy shift is completely different. And let me present the result, which is valid both for electrons, for electronic atoms, for muonic atoms. So instead of the Zimach radius, this delta E5, which can be also interpreted as a two-photon exchange, is a contribution. It's a sum of several terms. One of them is the two-photon exchange between the electron muon and the proton. So it is expressed in terms of the Frey radius of the proton, times Z, because there is Z number of protons. A minus Z is the number of neutrons. So there's also Frey radius of the neutron, which is below. What is interesting, also neutron contributes to the energy shift due to this, in general, charge distribution, because it has a significant two-photon contribution. And also there is this contribution Ri minus Rj. So this is for point, this formula is written for point nuclei, and this is the distance between the protons multiplied by power 3 and average with the nuclear wave function. And this is the true formula. For heavy nucleus, I would say it may coincide with the previous simplified formula, but even for deuteron, this term will vanish. And for deuteron, there is no this Frey radius. There is only this contribution for the proton and neutron, plus the so-called nuclear porosity contribution. This nuclear porosity contribution has completely different physics for electronic atoms, for muonic atoms. For muonic atoms, Simon has presented the formulas. Let me mention that in the different language, this nuclear porosity contribution can be written in terms of such a matrix element. Phi n is the nuclear wave function, D is electric dipole operator, and then it's a square root of Hamiltonian minus En. So this is something which we think we can calculate, and this is the main contribution to the porosity. There are many corrections, for example, coming from the spectral expansion, but in principle that can be calculated. For electronic atoms, this nuclear participation contribution is much different. And the reason comes from the relation of the lepton mass to the nuclear excitation energy. If the lepton mass is much smaller than the nuclear excitation energy, the probability shift takes this above formula. So it is d1 over h minus e and a logarithm of hn minus em times t. And this was calculated for deuterium about 20 years ago and maybe 30 years ago. So it is well known. But this formula also works for helium-like ions, lithium atoms, and this means a very good approximation. For ionic atoms, the formula we see is much different, and there are many more corrections because the nuclear structure contribution is much more significant for ionic atoms. As Simon has mentioned, delta Isc has not yet been calculated. Means for deuterium, we have some approximate value, which we think it is correct, but has not been confirmed. But for all other nuclei, this delta Isc has not been calculated because it is quite complicated. And how come we are able to determine the nuclear size from the atomic spectroscopy? The main reason is that the atomic spectroscopy from the nuclear point of view is extremely accurate. Means the typical uncertainty is about 14, 15 digits, like 1s2s in hydrogen, is 1s2s. So it is this precision means nuclear size is very significant because it is on the 5th, 6th digit. No, not a fifth. It means maybe a 10 digits, whatever. But it is very significant. So if you can predict, if we can present theoretical prediction of this accuracy, from the difference we can obtain the charge radius. And the shift due to the charge radius for hydrogenic system is just proportional to the mean square charge radius times the wave function of the region. This is the Z alpha 5 contribution, which is relatively small, almost negligible, and Z alpha 6, which here I calculated only using elastic contribution. It's also relatively small. And from the spectra in hydrogen spectra, in principle, we can determine the proton charge radius. In principle, because 1s2s is not sufficient. I will explain on the next slide why it is not sufficient. Similarly, for the Happy splitting, we can also determine the nuclear structure and obtain the Zmac radius. In fact, for hydrogenic structure, the hydronic contribution of the proton nuclear structure of the hydrogenic contribution is of the order of 10 to minus 5. It's much more significant. It was interesting to observe that the Happy splitting of hydrogen agrees with that of the anti-hydrogen. Means in principle, they should agree if the CPT is not violated, but it is very interesting to check that indeed the Happy splitting anti-hydrogen is the same like in hydrogen with the precision of 10 to minus 9, which is a good comparison. What is very interesting is to compare the Happy splitting hydrogen with the ionic hydrogen. The measurement of Happy splitting ionic hydrogen has not yet been completed. There are two groups working on it, but from this, we can obtain a very deep understanding of the magnetic interaction of the proton. I would say this is not well known. So far, the calculations from the atomic structure perspective are accurate only for hydrogenic systems, are accurate enough only for hydrogenic systems to obtain the charge radius. I had a project to calculate it for helium, and I will mention why, at which level we are for the helium. But for all other atomic systems, we are not able to determine the absolute charge radius, but only the charge radius difference in the isotope shift. And this is still pretty interesting. For hydrogen, if we are determining the proton charge radius for hydrogen, we need two transitions. One is the 1s2s, and another is 2s2 pi or 2s3s or 2s4p. Why? Because we need not only the charge radius, but also the Rydberg constant to determine two unknowns from two transitions. And to calculate this, transitions, we also have to perform some calculations. I mean, not only to solve the Dirac equation, but also to go beyond the Dirac equation to account for final nuclear mass, for some QED, and also for nuclear possibility, which for protons can be obtained from the inelastic inelastic electron proton scattering. Means it has been measured pretty accurately. We can obtain this from the scattering data. Inelastic scattering data, we can obtain this nuclear permittivity from ionic hydrogen. And what is interesting that from the isotope shift between the deuterium and the proton, the charge-ready difference, which is obtained from the electronic atoms, which is at the bottom here, agrees with the same charge-ready difference which is obtained from ionic hydrogen. And this is a very strong test that we very well understand the electronic structure theory and also this nuclear possibility, because the ionic deuterium in the ionic deuterium, the nuclear possibility is very large. And by the fact that we obtain the same charge-ready means the square of charge-ready difference, because it's completely different physics between, maybe not the different physics, but means different orders of magnitude. This agreement indicates that we well understand this nuclear structure contribution, at least in the ionic deuterium. However, we obtained here agreement, but it is known for since 2010 there is a strong disagreement for the absolute proton charge radius. Randolph Pohl will speak about this in his talk. What I want to mention here, that situation is not very clear because different transitions, for the first transition, we take the 1s2s. For the second transition, or 2s to p1/2, or 2s to 4p, we obtain a different charge ready. And this charge ready scatter from the ionic value to the previous hydrogen value. The only indication that this previous hydrogenic value was not correct is the fact that these measurements are only from one laboratory, and this one laboratory tends to larger proton charge radius. Here on the left, there have been different laboratories. The first one is Eric Hesser, another is Garching, and there's also Garching. So and also to SAD, there's a recent measurement in States. I don't remember exactly the laboratory. It indicates that rather the smaller proton charge radius is preferred, and because of that, the CODATA has assumed this. That the ionic hydrogen value is correct and then adjusted the fundamental constant to the ionic hydrogen value. What is interesting that not only the proton charge radius disagree, also the hyperfast splitting in ionic deuterium. The reason I'm mentioning it because in contrast to the isotope shift, we don't have a very good understanding of the hyperfine splitting. Because we have agreement for the isotope shift between the proton, between hydrogen and deuterium, but for the hyperfine splitting, we observe a disagreement. And to my opinion, it is because we don't have appropriate nuclear structure theory for the we don't have appropriate theory to describe nuclear structure contribution to the hyperfine splitting. There is this naive picture. If we assume that the nucleus is just a rigid ball with some charge distribution and magnetic distribution, then this nuclear shift is called Bohr-Weisskopf effect and gives the following contribution, minus 0.1177 megaelectron volt. But if I take the experimental value, which is measured by Randolph Pohl, subtract the theoretical for point nucleus, which is very simple to calculate, elementary, the difference is 0.966. It's of opposite sign. How come? Yes, because we don't have good understanding of the nuclear contribution to hyperfine splitting. The nuclear possibility, or this picture of this picture of the nucleus is described by the finite charge distribution magnetic distribution is incorrect. It's oversimplified. In the true picture, one has to take into account in the different approach. So it was in fact derived years ago by Lowe. So there was some Lowe contribution, some nuclear positivity contribution. We try to do it. I'm not nuclear physicist. I'm atomic physicist, but anyway, I try sometimes to use this nuclear physics model and to obtain the following result by taking into account, by completely neglecting Bohr-Weisskopf, using just calculate the nuclear structure contribution for first principle and obtain 0.383. It disagrees with the measurement, but it is at least of the proper sign, I would agree. So I would say at least partial success that I obtained shift in the correct side. In fact, this agreement is now almost the same like for proton charge radius. It's 5 sigma disagreement. So this is something I would say which I would like to point attention to our nuclear physicists to try to calculate the nuclear contribution to the hyperconductivity in deuterium. Deuterium is such a simple nucleus. Why not to calculate it and check if we have a good understanding of nuclear structure contribution to the hyperconductivity? This is not only one experiment where we obtained this agreement. I will mention the next one. This is the helium-4. Randolph Pohl will explain a lot about this experiment. I would like to point out that I had that we would like that we from the that proton charge, the alpha charge radius has been determined very accurately, and we would like to also to have such the similar derivation from the atomic spectroscopy. I mean, from the helium spectroscopy. We tried but failed, and the reason that we failed because the calculation of atomic energy levels happens to be a little bit too complicated. We performed the calculation, but we are not sure that our calculation is correct. What I mean the following. If I take the alpha charge radius as determined by Randolph Pohl and plug it to my calculation, I obtain the following result. This is the E2 triplet S, 2 triplet P theoretical prediction, and it in rather good agreement with the experimental value, which has been measured by Shuming Hu group in I forgot the laboratory in China, near Wuhan, but I have forgotten. It is in good agreements. So it looks like a confirmation of the Randolph Pohl, but it is not. The reason is the following, that we can, in the same approach, we have also calculated the absolute shift, absolute energy of 2 triplet S and 2 triplet P, which is in this middle column here. And we observe discrepancy with experimental values. And this discrepancy is of the same order, it's 0.4 megahertz, 0.4 megahertz. So although we agree for the difference, we disagree for the ionization energy of triplet S, triplet P. So most probably we have some mistake, but we don't know the source of this mistake, the calculation. We are checking it. It will take another few years to get it, but we aim eventually to get the charge radius from the helium spectroscopy. I mean, reliable number. Maybe it will not change much, but our result has to agree with other transitions to be sure that the result is correct. Coming back to the helium-4, helium-3 isotope shift, here is also a pretty interesting situation that one can measure in helium different transition, 2 triplet S to triplet P, and also 2 triplet S to singlet S, and the charge radius difference from these two transitions are different. We don't know why. So this, this has been corrected by the Rentgeling. So if we take so all these measurements give different value for the charge radius difference, most probably because we think that it's a mistake on the experimental side. It has not yet been confirmed. And this is the reason why we very urgently waiting for Randolph Pohl result for helium-3. We'd like to know how the muonic hydrogen charge difference compares to this electronic helium determination of the charge radius difference, because it is very to resolve which experiment is correct, which one is incorrect. Anyway, it is very strange that different transitions, different measurements give different charge radius. It should not be the case. It can be if there are some unknown forces. Maybe we are here probing some unknown forces. If the experiments are correct, it would be very interesting to confirm these transitions and remeasure and confirm, because maybe there is some interesting physics there. In the previous talk, I'm almost finishing. In the previous talk, we heard about the determination of the Zimach radius half-wave splitting. But before this, let me mention about another isotope measurement between lithium-6 and lithium-7. Here we also have different transitions, to P1 to S1 to P3 to S1 3S. And from all these three transitions, we obtain more or less results in agreement. They are less accurate, and maybe because of less accurate, somehow we obtained relatively good agreement for the charge radius difference between lithium-6 and lithium-7. But not for half-wave splitting, situation is little more, as I mentioned, is much more complicated. If you assume this very naive picture that the nuclear structure only goes through this so-called Zimach radius, then if we interpret the difference between the theory and experiment, this is the theory, below is the experiment. If we interpret the difference between the theory and experiment as the coming from the Zimach radius, then the Zimach radius for lithium-6 is 3.25, for 6 radius 2.30. But if we compare with the charge radius, the situation is opposite. The charge radius for the lithium-6 is much larger than the for lithium-6 and much smaller than for lithium-7. So this indicates that this picture that half-wave splitting, then the nuclear structure contribution to half-wave splitting comes from this Borovaskov effect, it confirms that this is incorrect picture. One has to take into account the inelastic contributions. So this commonly accepted picture of Borovaskov effect doesn't work even for such a simple system like lithium. And let me finish that there are some very important measurements which are in preparation. The most important is ionic helium-3, which I hope Randolph eventually will present. Also very important is 1s2s in helium plus. There are two projects. One is performed in Garching, another in Amsterdam. And this will be one of these very independent determination of the Rydberg constant, which also results in proton charge radius. Also very important is the ionic hydrogen measurement, because this would allow to compare the half-wave splitting in ionic hydrogen and electronic hydrogen. Okay, and also let me mention that there is still important to perform the scattering experiment with electron, proton, muon, proton. The last one is the direct comparison of electron, proton, muon, proton scattering, which is a project ongoing in PSI. It's called MUSE collaboration, and another one, Amber collaboration, which is a muon proton scattering at very high energies. It is the NIA66 project at CERN, and this should shed light on the proton size, proton charge radius discrepancy. Thank you very much for your attention.
All right, thank you very much. Are there some questions? Okay, we have 2 questions.
Yes.
Yeah. Maybe Jacek first, because he's the first one that I see on the. I'm sorry about this.
Yes. Yeah. Do you have any information about estimation the strong coupling constant value in deuterium nucleus?
I don't understand the question.
I repeat.
No, I understand the wording, but I don't understand the question, because there is no, we don't see the strong interaction couplings in the nucleus, because we always use some effective nuclear structure theory where we, in fact, this potential, I took the model potential, which has been derived from the proton-neutron scattering, very accurate, and that's all. I don't care about the nuclear, about the strong interaction coupling, because how it contributes to nuclear structure is very complicated. Nobody is, I think, able to directly relate nuclear structure to the strong interaction couplings. I don't think if anybody is able to do so.
No. Okay, I agree with you that this very complicated.
I agree, it's so complicated. Maybe it is possible, but not me. I am atomic physicist.
Yes, but I would like to ask one question.
Please.
Do you know any experiments where was measured the dependence of strong interaction between nucleons in deuterium nucleus?
Yes, but what does it mean you can measure? Because the strong interaction coupling is fixed. You cannot change it.
Yes.
So you calculate the binding energy and try to calculate from the QCD principles. That's all.
No.
I don't.
So maybe this is a question for the discussion session. Is there anyone else who has a question?
Okay, thank you.
Thank you.
Yeah, is there anyone else that would like to ask a question?
Yes, I have one very fast. So
okay.
You mentioned that you did a computation for the hypersensitivity ionic deuterium. Which nuclear model did you use for that?
Moment. Let me go there and I will tell you what I have done.
Was it the IVA?
Moment. No, it was moment. Let me go to the ionic deuterium. I'm trying to find. Oh, it's here.
This one. Yes.
That's the point. I use Jim-Fryer calculation for electronic deuterium for this leading contribution, which doesn't depend on the nuclear mass. And here the nuclear structure contribution. For nuclear permittivity, I use this standard, I forgot this 8018 potentials, and that's all.
Okay.
Because it was because the permittivity correction means relatively easy, like the contribution to energy. It's not very much different. But this leading contribution is called low contribution. I use Jim-Fryer calculation.
So I have a question. So when you then for lithium you were talking about, and I'm not familiar with the language. So for lithium you were talking about that like my understanding was that you essentially said that the naive assumption is that sort of the Seemach.
Yes. Let me repeat.
I'm just trying to understand the physics. So are you
exactly? So let me answer.
Is this the expectation? Is that with the energy scales? Does that have to do with the energy scales that you are essentially deeply bound nucleus versus in deuteron you have a lightly bound nucleus where you expect the continuum anyway to contribute more? Is that based on that?
Yes and no. In generally accepted paradigm, one assumes that there is some finite distribution of magnetic moment and charge density, and calculate the contribution to hyperspeedic, assuming rigid nucleus without any excitations. This is so-called Bohr-Weisskopf effect. And if we assume then this Seemach radius is given by the following. Certainly, there is some nuclear permittivity correction, but there is no theory for this. You don't know what formulas to use. For deuteron, I have derived these formulas and tried to calculate, but still I obtained this agreement. So let me summarize it, that we don't know how to account the nuclear excitations to the hyperfast speeding.
But
we don't know.
So if I take, okay, but I don't want to take too much time, but if I take NRQED, right, and this is
with NRQD I can do everything. But we are talking about here NRQCD or on the nuclear size.
Yeah, but
I can do everything.
Yeah, but I'm trying to say I can construct a theory where I have like NRQD couples the photon to the electrons, and then the photon coupling on the other side to the nucleus is given by matrix elements of currents. So I have matrix elements of vector currents.
These matrix elements are not well known. That's the point. They are not well known because there's such a strong cancellation. You have to take the magnetic interactions mostly, and they are not well known. This naive picture, for nuclear, for the correction to energy shift, they are known. But for magnetic interactions, they are not well known. Okay, maybe you can include this, but I mean, it's one has to include relativistic correction to the magnetic interactions to account for this.
Yeah, I appreciate that, but this is what Simone.
I
suppose Simone. So this is not.
No, but
maybe we talk about.
Simone was talking only about contribution to energy shift, not the hyperfast speeding. But for the hyperfast speeding, the theory is completely different.
Yeah, but
much more complicated.
Yeah, but those currents that he's using, they have been developed to order.
Yes, but one has to use much more accurately and account relativistic correction to the current.
Okay, the relativistic monoband corrections are in those, right? In the chiral EFT current. So
yeah, no, but I try to follow this, and then means it is not so simple. It means it is Jim-Fryer tried to calculate for deuterium, for electronic deuterium, and even for such a simple system like electronic deuterium. It was
so I would like I would like to quantify this tomorrow, so we'll keep that in mind.
Very good.
Maybe
What time tomorrow?
In the discussion session, we'll simply just talk a little bit about numbers. How about that?
Please.
And talk.
If you want to quantify, but this is the good here that the ZMAC radius you obtain is much different. Good. We'll continue tomorrow.
And then the next talk.
Today I will talk about the nucleon and nuclear structure from our measurements in mostly muonic atoms, which is already a bit old, and what are the next plans to do what we're doing. So the proton radius puzzle is now, more than 10 years old, and you've probably all heard of it, that it looked for some time that there's an exciting 5 to 7 sigma discrepancy between the 0.88 femtometer RMS charge radius determined from electron scattering and hydrogen spectroscopy and our measurements in muonic hydrogen. And the reason why our error bar is so much smaller is, of course, that the muon's mass is 200 times of the one of the electron. And so this picture is vastly not to scale, because the Bohr radius in muonic hydrogen is 200 times smaller than in normal hydrogen. And the finite nuclear size effects and all nuclear properties show up with the 200 to the third power, which is a few million times enhanced in muonic atoms. So muonic atoms are indeed the ideal probe for nuclear properties, I would claim. Muonic hydrogen, there's this level scheme. You have to know the lamp shift, and to show you what this means. In muonic hydrogen, we measure the 2s to 2p transitions, and you see the vacuum polarization, QED effects, and mostly vacuum polarization move down this 2s level to the red dashed line. And then there's a macroscopic shift, which accounts to 2% of the energy splitting here. So this is really huge. And so we don't actually have to measure very accurately to determine the charge radii, vastly more accurate than by other means. With a big caveat, of course, and that is what we're talking about. We've been talking about all over the day, these nuclear polarizability contributions of various kinds. This proton radius puzzle looks like it's solving itself by more measurements. And you see that the situation at the moment is the muonic atoms. So you can also use muonic deuterium and the isotope shift to determine a proton radius. This agrees very nicely with the muonic proton radius from our last paper. The shift from our first paper to the second paper is just because of updates in theory. And then there is our measurement in Garching of the 2s4p transition, the 2s2p transition, the classical lamp shift measured in Toronto, p-rad elastic electron proton scattering at very low q square. So this looked like everything is in order if it wasn't for these 2 points here, which both measure the 1s3s transition in Paris and in Garching. And the most recent result from Colorado State University by Dylan Yost's group, who measured the 2s to 8d5 half, which is part of this this older co-data point, and it lies in between. So there may be still a problem, and this may have various origins. I would just like to note that all of these measurements here, which agree in atomic physics, they all measured S2P 1 photon transitions. Okay, so this is muonic hydrogen 2s2p, muonic deuterium 2s2p, 2s4p in hydrogen, 2s2p in hydrogen, and the S2S and S2D 2 photon transitions seem to have probably an unaccounted for systematic effect, which may not be the same for these 2 measurements, or in fact it actually may still be some unaccounted for theory contribution that shifts S and P and D states differently. So it's maybe not yet solved, but there is a motion towards smaller radii, I guess, and in particular with this elastic electron proton scattering measurement here. Okay, so why is the proton radius so interesting? Indeed, it's interesting because you have various means to determine this proton RMS charge radius, right? You can do spectroscopy in hydrogen, as we've seen a couple of times. You can use elastic electron scattering. We have used muonic hydrogen in all determining this quantity proton charge radius. There's going to be muon scattering experiments both at PSI and at CERN. And of course, you can do lattice calculations and also come to get form factors and then do the extrapolation, determine the slope of the form factor and determine the charge radius. So this is a nice thing, that you have various means to determine the same quantity from different measurements or theory. And it involves QED to some orders, low order in Munich hydrogen, very high order in hydrogen. It contains nuclear polarizabilities, just the other way around, right? For Munich atoms, they are much enhanced compared to normal atoms. And you can test QED and the standard model by comparing different means of determining the same quantity. And I will come back to that slide later when I lay out what may be the future of this. In the same measurement campaign more than 10 years ago, we've also measured Munich deuterium, and we have heard very nice talks by Simone and Christoph about the polarizability problem in this, so to say, only weakly bound nucleus. And this is a very busy plot, but I'll walk you through this. Here you see the same 5 sigma discrepancy that you saw for the proton charge radius. Here now you have the deuteron charge radius and the co-data 2014, which was basically given by hydrogen and deuterium spectroscopy and elastic electron proton scattering. Because of the isotope shift, you can get the deuterium radius out of it. Electron deuteron scattering is unfortunately not precise enough to distinguish between these two values. And when we first published our paper in 2016 on the deuteron radius from Munich deuterium, there was a small 2.5 sigma difference between this deuteron radius and the one that we expected from taking the proton radius from our Munich hydrogen measurement and the electronic isotope shift of the 1s/2s transition, which we've measured in Garching. So there seemed to be a suggestion for future work. And as you see, our theory colleagues have been very active. And now in the most recent paper by Sonja Backer's group, there's perfect agreement between Munich deuteron radius and what I would say is the real value for the deuteron radius from proton radius in Munich hydrogen and the isotope shift. Here's this very nice formula where you get the difference of charge radii of the deuteron and the proton, where you get the very precise difference value with these 2 and 3 photon contributions in place. You also see that these 2 error bars that I indicate here, the inner one is the experimental one, and the outer one is this lighter red, is the theory uncertainty, which is from 2 and 3 photon exchange. And it turned out that the 3 photon exchange contribution for the nucleus is significant, and but there's been good progress in reducing this error bar. Now you can do various things, right? So we have our formula that many of the theory colleagues calculated, these very well calculated QED terms for the lamp shift. Then there's the 2 and 3 photon exchange contribution. And then there's the finite nuclear size contribution. And we measure the left-hand side of this formula, and then we can determine something on the right-hand side. The classical way to do that is you take the theory of the 2 photon and 3 photon exchange effect, and then you can determine the charge radius. And this is what I did for that plot here. There you see the result on that. But you can also turn this around by taking this number, this very precise value for the deuteron charge radius that you get from the proton charge radius and the isotope shift. You can plug this into this formula here, and then you can solve for this 2 and 3 photon exchange summary, and for that you get the experimental value for the nuclear polarizability and the theoretical value. And this used to be a factor of 4 different, but due to the sustained work of our theory colleagues, this has shrunk now to a factor of 2. So I would argue that this is maybe also a very good observable or benchmark for these polarizability calculations. If you have charge radii and muonic atom measurements, then you may exploit this fact. Okay, Munich helium, Christoph said it already. I can still only present the Munich helium 4 result, which was published last year. We have still not found the time to think about how to deal with the 3 photon exchange contribution in Munich helium 3. We have to sit together, Christoph, and do this maybe next 2 weeks or so. You see that this formula now goes up. Both the QED part goes up, the nuclear structure calculations explode, but also the coefficient for the nuclear charge radius coefficient explodes, and therefore we get an even. We have now a 30% effect on the lamp shift, which comes from the finite nuclear size, not only 2%. So we're getting more and more accurate. And this is the data that we've measured with a fit to that data, which takes into account various systematics on each individual point here. And we've measured these transitions. So we can again determine the lamp shift, from which you get a finite size shift. But we also can determine the fine structure and the 2s hyperfine splitting. That's how we chose these three transitions that we measured. The preliminary result is that our experimental uncertainty is a factor of 10 better than the theory uncertainty. But this theory uncertainty is already quite small. So thanks to the effort of the various people involved. You see, there's perfect agreement with the world average from elastic electron scattering. It's just because of this, because I blew up this scale so much that this looks like it's not very good. In fact, this is a very good value from elastic electron scattering. It's just that Munich helium-3 is even better. And then for Munich helium-4, the 2 and 3 photon contribution has been estimated. It's our educated guess based on Pachucki's paper, and Christoph helped us with our educated guess. Sorry, I have to close the door. And so from that, we get a significant uncertainty from this uncalculated 3-photon exchange here, and the calculated 2-photon exchange from the Bakker group and others. And this gives our value for the helium-4 charge radius. Here you see our spectra, which we've taken in the 2s-2p transition, compared with the predicted position. So there's no discrepancy whatsoever in Munich helium. There's our second transition, and it agrees very nicely. I would like to point your attention to these 2 points here, which was the old CERN experiment in the 1970s, which claimed to have seen resonances at this position and at that position. And for that, you don't need any theory, right? You just compare their laser wavelength with our frequency, laser wavelength or frequency that we've measured. And so their line was found at a completely wrong position. Interestingly, so there were questions from the beginning, because they measured a very high target gas pressure, and many people thought that this cannot result in long-lived 2s states, which you need to drive this transition. Oops. But nevertheless, this point is still around in literature. And in fact, the charge radius that they got is not so far away from ours, because it was this wrong measurement was using insufficient or incomplete theory, and they got a not so wrong charge radius out of it. I would also like to point out that my colleagues at PSI in 1992 showed that there is no resonance line in this region, but they could not give an alternative position because they could not scan further, because the PSI proton beam was rebuilt at that time, and then they concluded it's doesn't make any sense to rebuild the complex laser system. So I would like to conclude that Munich atoms and ions provide 10 times more accurate charge radii of the lightest nuclei if you combine them with the calculated polarizability. And if you have some good charge radius from regular atoms, for example, then you can use the Munich atoms to determine the nuclear polarizability with, it used to be few times, now it's twice more accurate for Munich deuterium. So you really get a handle on these interesting few nucleon properties. So I showed you this slide before, where I said the proton charge radius, it's not a fundamental thing, right? But it's interesting because you can measure it by different means. And so I would expect that in the coming years, we can do the same with the Rydberg constant. The Rydberg constant is much more fundamental, even though it's not really fundamental. And it can be used to test QED in the standard model, because you can measure it by various means, right? Today, we can determine it from hydrogen. If we plug in the proton radius, for example, from Munich hydrogen, in the 1s-2s transition, then we get a Rydberg constant. You can determine it from deuterium. You will be able to determine it from helium plus hydrogen, like helium, when the experiments are done, which are going on in various places, like Amsterdam and Garching for the helium plus. Okay, but you can also use these molecular ions, or helium atom or lithium plus, as we just heard this talk today, if you have accurate 3-body QED calculations, and you also need to have these charge radii, and then you will be able to determine the Ripple constant from molecular ions, from atoms, and what Christoph just said, and from lithium. So we need a lithium nuclear charge radius, and we're thinking of ways to do that from Munich atoms. And going further, right? If people come up with 4-body QED calculations, very accurate ones, then you can use H2HD, the lithium atom, or the beryllium ion. Of course, then you will also need a beryllium charge radius. And then, of course, you can do this with purely leptonic systems, muonium, positronium, with highly charged ions, or with Rydberg atoms, and various other means. So I guess testing QED and the standard model by comparing different nuclear charge Z or masses or lepton types may be a way forward of doing precision tests of QED and the standard model. But of course, this absolutely requires precise nuclear charge radii and polarizabilities. And so you get this interconnection that you all know between the charge radius, the polarizability, electron scattering, the intense nuclear theory, precision spectroscopy in normal atoms and ions and molecules, and the muonic ions. Okay, what next? So if you look at this chart of the nuclear charge radii, you see that the triton has a very not so favorable uncertainty here. And we think we can ultimately do this a factor of 400 better if we get to a 1 kilohertz measurement of the 1s-2s transition in normal hydrogen, not muonic, normal hydrogen. That's what we did when I was still in Garching for hydrogen deuterium. We actually measured this on the level of 100th of a kilohertz. So with a measurement that is a factor of 100 worse than what we've done for hydrogen deuterium. We can improve this triton charge radius by a factor of 400. We're looking into ways of taking at the moment a slow hydrogen beam and trapping them inside a buffer gas in a magnetic trap, using lithium as a cold buffer gas, and then we want to shine a laser on it. This, of course, takes quite a while until we can do that. So we took a step back recently and started to do optogalvanic spectroscopy in a cell. So you put a gas in here and you do a microwave discharge to produce atomic hydrogen at the moment. And then we want to do laser spectroscopy with using a 243 nanometer laser. And of course, we have large pressure shifts and whatnot, but I hope we can model this for hydrogen and deuterium, because there we know what the answer is on the level of 10 hertz. And if we get an extrapolation which is correct on the 100 kilohertz level, then we could still improve the nuclear charge radius in this first step by a factor of, say, 4. So that's the way forward, what we're doing in Mainz. And the Kramer collaboration at PSI is now looking into the magnetic structure of the proton, as Christoph already said. So we're looking into the hyperfine splitting of Munich hydrogen, which is, of course, if you look at in the normal hydrogen atom, this is the famous 21 centimeter line. That's how you look into the sky, where you see the clouds of hydrogen in the sky. And this is the spin flip transition of the ground state hyperfine splitting, which has been measured 50 years ago already using a maser in normal hydrogen with 12 digits of accuracy. So this was the result 50 years ago. And still today, you can only use like 6 digits or so of this as a comparison with QED. So as a test of QED, because of these unknown proton structure effects. This is now the proton size is now the Seemach radius that Christoph already talked about. And of course, the polarizability for the hyperfine splitting, which involves the spin dependent part. The Seemach radius, as you know, is this funny convolution between, in a non-relativistic picture, between electric charge distribution and magnetization distribution. But you can also formulate this in terms of form factors and momentum space, and therefore you can also measure this using electron scattering. So you again have this access to the same quantity from electronic atoms, muonic atoms, and electron scattering. So we have actually done a measurement, a very crude measurement of the hyperfine splitting of the 2s state, by comparing 2 different measurements of the lamp shift. The lamp shift itself is sensitive to the charge radius. This was what I showed you before. And but we are limited by the 2p state level lifetime and that sets our line width. And if you subtract two very similar numbers with large uncertainties, then you don't get very accurate for the 2s hyperfine splitting. But in the ground state, you don't have that problem, and therefore we are aiming for the ground state. So this is a measurement from the 21 centimeter line, depending on the polarizability. You get this uncertainty. Then two different ways of evaluating the elastic electron-proton scattering result. And here is our, as I said, crude measurement from muonic hydrogen lamp shift transitions. And our goal, so here is the data for the proton charge radius. And if you you have these two transitions, and if you subtract these two from each other, using the very well calculated 2p fine and hyperfine splitting, you get to this 2s hyperfine splitting. As I said, the line width comes from the 2p state lifetime, so we have to go to the ground state. Our goal is to improve this by a factor of maybe 100, depending on the theory for the polarizability. And in fact, we're not the only ones. There is also a group at Rutherford Appleton Lab called FAMU, and there's a collaboration at J-Park in Japan who are aiming for this. And we have the same goal, but very different experiments, because this is a really difficult experiment. And it's very difficult to detect the flip of a single muon spin in a target gas. So the hyperfine structure in muonic hydrogen is this QED part, and then you have these two photon exchange effects. This is the elastic part, which is the Seemann radius, and then there's the inelastic polarizability part. And we will be able to obtain the sum of these two with 3 times 10 to minus 4 relative accuracy, because we intend to measure this one here with 1 ppm relative accuracy. And then this sets the scale, and the unknown calculated stuff sets the scale for the 2 and 3, for the two photon exchange contribution. And if we do this, then we can either, if we take Seemann radii from scattering or from hydrogen, we can determine the polarizability with relative accuracy of 10%, which you then can compare to theory. Or if you take the theory value for the polarizability, we can determine the Seemann radius and compare it with the scattering result or the hydrogen result. And using a model, you can then determine from the Seemann radius the magnetic radius. But for that, you need to employ a model for the charge and magnetization distribution inside the proton. We are getting ready for this experiment, and we hope to do a first real serious attempt at this measurement next year. At PSI, everything was of course delayed because of COVID. Otherwise, I would have maybe even had the chance to talk about this. This is a very difficult experiment. We have to scan over a large range of values because of the uncertainty in this term here and in the Seemann radius. So the position of this resonance is not very well predicted. So we have to scan a lot. And with that, my group in Mainz and the Kremer collaboration would like to thank you for your attention, and I'm happy to answer questions.
Thank you. Are there any questions? Don't see.
Good. That means my talk was loud and clear.
So let me then ask you the question, because if there is no, then I would take a chance. May I?
Yes.
So you have also 3 photon contribution here to the hyperfine splitting.
Well, that you have to tell me.
Okay, good. I have not thinking too much about this, but there is as well. So what you would then measure, it will be a sum of 2 photon and 3 photon contribution.
Yes.
But anyway, you will get a variety of results for this sum.
Yeah. And well, I mean, even if we cannot determine independently the Seemann radius and the sum of all n photon polarizabilities, maybe there's a way that theory can predict the evolution if you go from hydrogen to muonic hydrogen, which is basically
to my opinion, this is the most important thing, to compare electronic and muonic hydrogen, because if you obtain some kind of discrepancy, I'm very much eager, to find some new interactions. So if you observe something new, there's some discrepancy, it would be great.
Well, there's a discrepancy between 1 and 2 photon transitions in hydrogen.
Maybe with the Paris and Munich, you know what you mean?
No, I mean the most recent measurement from Colorado is also.
Yes, but it's only just one measurement.
No, but it's, I mean, all older co-data results were all based on two photon transitions.
So
now is one photon.
yes, but my point of view that you determine the center of the line, which is wide, with 10 to minus 5, 10 to minus 6 precision. It's always have a doubt.
So what we did in Garching with the 2s4p transition was 10 to minus 4 of the width, and that's when all this quantum interference came into play, right? And it's getting more complicated if you go to these two photon transitions. And so my guess is that it's probably another yet undiscovered systematic effect, and people are thinking very hard on how to do that. But eventually it may also be some missing, I don't know, delta L, something like delta L1. For p states, there's a difference, or for S and D states, QED.
Yes, but this is, no, the QED theory is very simple. I don't expect anything. No, it's very simple.
Okay,
it's very simple.
I trust you.
But anyway, it's interesting. Yeah, I agree. It's also interesting to see these discrepancies. But let's allow them to confirm it.
I think the Ripper constant is a beautiful way to do that, because
1s2 is in helium plus. 1s2 is in helium plus. This would be very good.
Yes.
Once they complete it.
Yes, and once you have found the problem in a theory experiment for helium as well.
Yeah. Yeah, but it will take some years. It's not so
well, simple. Nothing of this is easy, right? The simple stuff has been done.